f of x has a factor of x minus k if and only if, remember that in geometry was a biconditional, meaning this definition works both ways, if and only if f of k equals 0. So let's just take a quick minute. What did f of k mean earlier in this chapter? F of k. You are substituting k in for x, and f of k represents y, right? So I would say this. This is saying f of k, that's your y when x equals k. Remember, f of x is y for a given x. It's just a fancy way to write y. So when we say f of k, we're just saying that's our y value for whatever k value we have. Notice that k would be the 0 of this linear factor. We might also remember, we talked about this on the day we talked about the remainder theorem, where when we said f of k was the remainder. So we're basically saying, in other words, that x minus k is a factor if the remainder equals 0. Because if you go back to your remainder theorem, the remainder is f of k. So it seems like they're using these really mathy things in the definition, trying to sound like extra smart and everything, right? But it's just talking about the remainder that's left over. And that should really make sense to you. Like, think just about numbers, right? What are the factors of 12? 1 and 12, 2 and 6, 3 and 4. Why don't we choose 5 to be a factor of 12? Because if we divide it, it would have a remainder. It doesn't go in nicely, right? So factors are things that go in nicely. Factors are things that give you remainders of 0. So that's all the factor theorem says. So in the first box, we're just going to check if something is a factor. So read the directions in the first box. It says, determine whether x minus 2, this linear factor, is a factor of this polynomial. Well, if it is a factor, when I divide it, I will have no remainder, right? That's the only way it's a factor. So we're going to do polynomial division, and we're going to check for a remainder of 0. If you get a remainder of 0, you can say, yes, it is a factor. If you get a remainder of anything other than 0, you say, no, it's not a factor. It doesn't divide nicely. So I'm going to set up my synthetic. If we're dividing by the linear factor x minus 2, what do I put outside of the synthetic box? The positive 2, right? Set it equal to 0. What's the 0 of that linear factor? It's positive 2. And then I'm going to look over my polynomial. It's a cubic polynomial. It's x cubed. That's the highest exponent. So I have to have an x cubed, x squared, x, and a number term. And I've got all of those, so I can just drop in the coefficients. 4, negative 21, 9, 34. And then we just run through synthetic. Okay. So remember, drop the first term to get 4. 4 times 2 is 8. Negative 21 plus 8, what is that? Negative 13. Times 2 is negative 26. Plus 9 is negative 17. And negative 17 times times 2 is negative 34. I got a 0 remainder, didn't I? That makes me so happy because that means x minus 2 is a factor. So I'm just going to write that down. Yes. X minus 2 is a factor. Cool. So we're kind of leading up to this idea of like, what if a polynomial doesn't factor? Can we still find its zeros? Can we still find a way to find factors? And the answer is yes, through polynomial division. Okay, in the second box, we're going to show that x minus 2 a different polynomial. It's a quartic polynomial. And then we're going to go a step further after we show that it's a factor. We're going to factor everything completely. So see if you can set up your synthetic box for me. Let's put our phones away and set up our synthetic box. Okay, be very careful with this one. Make sure you have all the terms in the polynomial. Because that polynomial f of x was quartic, fourth degree, I have to have a term for every possible x term. X to fourth, x cubed, x squared, x, a number. So do you notice you're missing which term? X squared, so you've got to put a 0 there. So we'll have 1, -2, 0, -1, +2. Some people, I'll hand back your quizzes today from earlier in the chapter, and some people miss that. Like if you're missing a term, you got to put a 0 there. So make sure you have that in your notes. All right, add down and multiply. So we're looking for a 0 at the end. We're expecting that. We're going to get 2, 0, 0, 0. This is not very exciting. 0, finally, -1. And -1 times 2 is -2. Did it work? Yeah. So this, we've verified that it is a factor. We've shown that it's a factor because we're showing that has remainder 0. If you want to show something's a factor, you just have to show that there's no remainder. Okay. Now we want to factor it completely. Okay, so factor completely. So what that means is write out f of x not as the separate terms that are being added together, but as their factors, the things that are being multiplied together. Well, we just verified one factor, right? Which one did we show worked? X minus 2. So one factor is x minus 2. Okay, it works. The other factor of that polynomial is your quotient. Remember, your quotient times your divisor gives you the thing that you divided. So if these were x to the fourth, x cubed, x squared, x, and a number, remember when we divide, they're always one less. So this is now x cubed, x squared, x, and a number, and of course this 0 was my remainder. So I can say that the other factor must be 1x cubed. I don't really have to include the 0 terms, minus 1. So the factor that you checked is a factor, and the quotient of your division is a factor. Is that factored completely? No, x minus 2 is good to go, but x cubed minus 1, that's a difference of perfect cubes. That's the one you learned yesterday, so if you want to flop over to difference of perfect cubes. Okay. Difference of perfect cubes, I'll write it up here over on the sideboard, but that's a cubed minus b cubed is equal to the quantity a minus b times a squared plus ab plus b squared. So we just need a factor that x cubed minus 1. So like a cubed is x cubed. What's a? X. And b cubed is 1. What's b? 1. You never have to worry about the sign. So like don't worry about like is the cube root of -1, -1. You just treat it like a 1 because the signs in the other side do all the work for you. So you never have to think about one of them as a negative. You just treat it like absolute values. And so we got to plug those in. Let's see, I'll do that over here on my smart board. So okay, I've got my x minus 2 factor, and then the first factor in perfect cubes is a minus b. So that's going to be x minus 1 And the second factor is the a squared plus ab plus b squared, which that would be x squared plus x plus 1. See if I can get it to go over so I can see it a little better. Okay. Now you would look that over. Is that factored completely? You might check this quadratic, but we also had a conversation yesterday about the sum and difference of cubes. Does anybody remember what I said yesterday? Like, what would happen to your solutions for this quadratic part of the sum and difference of cubes? Does anybody remember what we talked about? Like yesterday I mentioned something, if you do the factoring by sum and difference of cubes, something special happens with this part. Like your answer is always, your discriminant is always negative, so your answers for the quadratic are really imaginary. Okay, so if you have imaginary solutions to that quadratic, you're not going to be able to factor it. Like, do you have factors of 1 that add to make 1? No, because factors of 1 add to make 2, or negative 2. So that one, if you know that's always imaginary solutions because your discriminant is always negative, you never have to check to see if you can factor that quadratic. Like, you know it won't factor because it has imaginary answers. So that's completely factored right there. Oh, sorry. Okay, questions so far? Anything you want to clarify? I'll say probably like the most common thing that people end up losing points for on a quiz or a test when I ask this kind of question, show that something is a factor, then factor completely, is they do the division, they show it's a factor, and then they only use the quotient and they factor the quotient. And so their answer may just be like x minus 1 times x squared plus x plus 1, but they forget to put back the factor that they checked. So remember, to really be f of x, which was a quartic polynomial, you have to have the x minus 2 factor in there as well. So don't forget to put back the one you checked. Okay, last thing that we want to talk about is solving quadratics, solving polynomials. I'm half reading the board right there. So it says in the third box, just like quadratics, you could solve polynomials by factoring. So there's basically 3 short steps to solve by factoring. Everybody should know this. Step 1, factor. You're going to be like looking at the other side of the green sheet. Is it 2 terms? Try perfect squares, perfect cubes. Is it 3 terms? Try a trinomial, guess and check. Is it 4 terms? Try factor by grouping. Did I check for greatest common factors? Like, you go through all those steps. Step 2. After it's factored, set your factors equal to 0. So all the factors that have x in them need to be set equal to 0. And step 3, at that point, you should be able to solve for x. If you can't solve for x, then you probably haven't factored completely. Like, you could continue to factor. You may end up at some point in this chapter with like quadratics that don't factor as your end factors, just like that one above. Well, then you would do quadratic formula if you wanted to find the imaginary solution. So remember, you have quadratic formula as a tool. Okay, and then what do real solutions show up as on your graph? The x-intercepts. Okay. That all goes back to that idea of we're saying these things are factors because their remainders are 0, and previously in section 4.3 we said that the remainders were the y values, so if your y value is 0, you're sitting on the x-axis. Okay, so all of the real solutions show up as x-intercepts. I know that I've kind of like written over the example that we're going to do for solve by factoring, so I'm going to rewrite that one. Is that 48 x to the 5th? Okay. Sorry, I'll get there eventually. 48 x to the 5th. So I'll rewrite that. One moment. Oh, look, it all came. I was being impatient. 48x to the 5th. And that's minus 3x. Okay. So you're going to solve this polynomial by factoring. It's a quintic polynomial, quintic polynomial, okay, because it has degree 5. So what are you going to do first to factor? What do you notice? Take out a 3, take out an x. They have a greatest common factor. If you're looking at this like this polynomial has 2 terms, you might check your list of perfect squares, but these are not perfect squares. You might check your list of perfect cubes, but these are not perfect cubes. So you're not going to be able to use those 2 for 2 terms. So you got to check for greatest common factor. You can take a 3x out of both of them. That leaves me with 16x to the 4th minus 1 equals 0. Is it completely factored? No, because now you look at your 2 terms. 16, x to the 4th, 1. Those are all on the list of perfect squares. So these are perfect squares. So perfect squares just factors out into 2 binomials, a plus b, a minus b, where a and b are the square roots of the 2 terms. So what's the square root of 16x to the 4th? 4x squared. So that's our first term. And of course the square root of 1 is 1. So the 2 factors really look exactly alike except for 1 is plus and 1 is minus. That way your outside and inside terms would disappear. Okay, so you don't have any x squared terms. Okay, is that factored completely? No. 3x is good to go. 4x squared plus 1 is good to go. But 4x squared minus 1 is another difference of perfect squares. Okay. Now note that 4x squared plus 1, that's a sum of perfect squares, but those don't factor. We're going to see this here in a minute when we solve. But sums of perfect squares always have imaginary solutions. They don't factor. Okay, so we're going to factor that last one again. We're going to keep the 3x. We've got the 4x squared plus 1. And now we're going to do another difference of perfect squares. So the 2 factors are going to look exactly alike, except have opposite signs. What's the square root of 4x squared? 2x. And of course the square root of 1 is 1. And then 1 is a plus and 1 is a minus. Now when I look over all my factors, they're completely factored. Like there's nothing left to do for the 2 terms. No more difference of perfect squares or cubes or anything like that. Okay, so we factored it. There's step 1. Now we're going to set all of our factors equal to 0. So 3x equals 0, 4x squared plus 1 equals 0, 2x plus 1 equals 0, and 2x minus 1 equals 0. So we're on step 2. Set them all equal to 0. Basically, anything that has an x in it, set it equal to 0, and then solve. This one, I would just divide both sides by 3, so x is 0. I have an x-intercept at the origin. That makes sense because that original polynomial had a 0 constant, so it has a y-intercept there too. I'm going to skip to the last 2 because these are linear, so they're going to be easier to solve. If I subtract 1 from both sides, and then I divide by 2, Then I have a solution at x equals negative 1/2. And on the last one, I would add 1 to both sides and divide by 2. So I have a solution at positive 1/2. And for the last one, I've got to solve for x squared. So I have to subtract the 1, divide by 4, and it's x squared equals, so I take the square root of both sides. A couple of things to remember back from chapter 3. If you square root to solve, you have to add a plus or minus. If you square root a negative, your answer is going to be a imaginary answer, so we'll have an I in our answer. And if it's a fraction, remember you can treat it like the square root of 1 over the square root of 4. You can break it up for division. And so this is really plus or minus 1/2 times I. You write I times 1/2 or I over 2, that's all the same thing, so you really can't go wrong. 0.5 I is the same. Okay, how many solutions do you have? One, 2, 3, 4, 5, right? There's 2 imaginary solutions right here. Positive 1/2 I and negative 1/2 I. So I have 5 total solutions, which solutions we sometimes also call zeros. Let's just take a trip back to the very first section. Total number of zeros of a polynomial is equal to the degree. What was the degree of this polynomial? 5. So we found all the solutions? Yeah. So that's something we're going to get to later as well. Like, how do you know you have all the solutions that you need? Because you have as many as the degree. Okay, questions, concerns? You know, if you're going to graph those, 3 of them are going to show up on the graph, 0, 1/2, negative 1/2. The imaginary ones you're not going to plot. Okay, so you'll see that this graph only crosses the x-axis 3 times. Never make that graph cross more than 3 times, because then you're adding in a real 0 that doesn't exist.
Is it possible to graph imaginary numbers?
On an imaginary plane, yes. So like basically when you're graphing imaginary zeros, you take your normal xy plane and you treat it like a flat surface. So it becomes, so we can do it 2D, and then the imaginary axis is like 3 dimensions. So it's sort of like 3-dimensional graphing, but it's not really real in space. So yes and no, of sorts. But what you'll notice when you have imaginary solutions in a polynomial like this is like somewhere else in the graph, not at the x-axis, the graph does something like where it turns above the x-axis, or it has like some kind of strange bend to it that, like, why would you draw that? Because there are some imaginary zeros at play. But like we don't have enough information right now to make that happen. Okay, we just know that they don't show up on the x-axis. But yes, you can graph them. It's a whole part of fractals and really cool things. We're just not ready for it. Okay, you have a homework assignment.